Hello, my name is Micaela Jurado, and today we're going to discuss Lab 5 Magnetic Molasses. So, the purpose of this experiment was to collect observational data of a magnet falling through a conductive tube of aluminum foil, model the magnet tube interaction computationally, and compare the computational predictions with the observed data. So, here are the physics principle we're going to use. We're going to use Faraday's law, which discusses the EMF produced on an object. The magnetic field produces an EMF on the object. Lenz's law, which is the induced current flows opposite direction to the change of induction. This is the formula. Biot-Savart's law, which describes magnetic field generated by constant electric current. This is also the formula. And we're going to use Newton's second and third law, which here are the formulas. And so for this experiment, this is the model we used. We practically dropped a bar magnet through a tube of aluminum foil, and we would time how long it would take for the bar magnet to come out of the tube. So it would have two forces on the magnetic dipole, because we're assuming it's a magnetic dipole. We have force magnetic and force gravitational force. So yeah, these are these two, and we also ignore air resistance. So these are the experiment details. We have that the system is the bar magnet and the aluminum tube, and the surroundings is Earth and everything else. The length was 0.3, the width was 0.006, the inner radius 0.026, and the outer radius 0.032. Here are the magnetic properties. This was the mass of the magnet, and this was the mu of the magnet. And then per 5 trials, our average time was 1.254 seconds. So here were the computations for our formulas. This formula was computed by this, and this formula is practically for the magnetic field of bar magnet, and this one was for magnetic flux. So these are the computations. And then here we calculated all the forces, which we said is magnetic force and gravitational force, and we add them up and we get the net force. And with this net force, we can adjust and update the velocity and position of the bar magnet in the computational model. Also, this is the formula for the force on the ring, which is the tube. And this is visualization and computational data. So this was what we obtained from our computational model. And from 0 to 0.1 seconds, force gravity was bigger than force magnitude. From 0.2 to 0.7, gravity was equal to force magnitude. And when it was from 0.8 and lower, force gravitational was bigger than force magnitude. And so this is interpreting the simulation. It says which color corresponds to the counterclockwise current and the clockwise current. And by using Lenz's law, red was counterclockwise and blue was clockwise. What happens if you flip the magnet? The magnet will fall as before, but the current directions would be flipped. So how does the real world compare to the computational? This is change of time. Computational is slightly shorter, so it accounts for air resistance, and human errors can improve accuracy. And also, how does the plot shape tell you about the forces acting on the magnet? Gravitational force is greater than magnetic force when entering and exiting the tube, equal and within. Okay, so this is the possible errors. We could have measurements such as stopwatch not being accurately stopped, friction such as the magnet hitting the sides of the tube, and air resistance. So these are my discussion questions. It says, what if the tube resistivity was close to 0? How would the magnet dynamics change? So from Ohm's law, decreasing the resistance will increase the induced current. So this is Ohm's law. It's B equal to I times R. And producing a stronger opposing magnetic field would slow the magnet even more. So what slots were cut into the tube? What if slots were cut into the tube? How would this affect the ring currents in your model? So the there would be like less rings of current, which will decrease the magnetic force, and the magnet will form much more faster. And so yeah, that's all for today. Congratulations on your last lab finally. Yeah, have a great rest of your semester and happy Christmas.